Bismillahirrahmanirrahim. Assalamu alaikum dear students. Welcome to the online lecture on MATLAB simulation of nonlinear control. Today we are going to discuss this paper on backstepping based dynamic surface control method for a class of non-lower triangular nonlinear systems. So the special thing about this paper is that for non-lower triangular nonlinear systems, the usual approach for backstepping based control does not work. So if you're not familiar with backstepping control or how backstepping control is designed, I will post a link on another video that I posted earlier that will help you understand what backstepping control is and how backstepping control is designed. But for now, for this video, let's focus on the control method that has been developed for a class of non-lower triangular nonlinear systems to which you cannot apply the usual backstepping based technique. So they have applied a different type of backstepping control technique. As usual, we will not go into the full details of the paper. You can download the paper and study this paper by yourself. We will be interested in the MATLAB simulation of the control that has been designed. So nonlinear systems considered in this paper are of the form xi dot equals some nonlinear function of all the states. That's why this system is non-lower triangular, because the derivative of each state is not it's not an integrator chain type of a system where x2 dot is equal to x3, x3 dot is equal to x4, x4 dot is equal to x5, and so on. It's a system where every derivative is involved, like all the states in general. So the last state involves the control input, and this is a single input single output system being considered in this paper. U is a scalar, and the first state is the output of the system. And here these functions are nonlinear functions which are assumed to be smooth for the reasons, of course, all the nonlinear control system students should know. If you don't know, then I have a playlist on my channel regarding the lectures on nonlinear control. You can start from lecture 1 and learn nonlinear control from there. A whole semester course is almost the whole semester course is there on that playlist. So reference signal will be denoted by YR, and it will be the reference signal and its derivatives are considered to be bounded. Notice that the control designed in this paper is only applicable under these assumptions. So these assumptions, this is also an interesting assumption that the nonlinear functions, the partial derivative of ith nonlinear function with respect to I plus 1 state is assumed to be greater than or equal to 0. That's because later on they rewrite this f star I as f star I minus xi plus 1 is equal to fi. So they redefine the system in equation 1 as in this format, so that the derivation of the control will be smooth and easy. In the derivation of the control, they define the tracking error S1 in the step 1. In the step 2, they define tracking error S2, which is x2 minus z2. Z1, z2, this is by reference. This is the desirable value of x1. Z2 is another variable, you can call it auxiliary variable. Its derivative is given by alpha 2 minus z2 over tau 2, where tau 2 is a parameter of the filter. So this basically, the backstepping control is based on certain filters. So you can see here that the first order low pass filter have been augmented with the control, where alpha 2 and z2 are input and output of the filter. So z2 is the output of the filter, alpha 2 is the input of the filter, and tau 2 is the filtering parameter. So there will be multiple filters used for the controller design. So similarly, there will be another filter here, a first order low pass filter, where z3 is the output of the filter, alpha 3 is the input of the filter, and so on. Alright, so keep going this way. The final control is designed U is equal to 1 over function g times minus kn sn minus fn plus z and dot, and there are some intermediate auxiliary functions as well. So for example, this there is z2 dot is equal to alpha 2 minus z2 over tau 2, and so on. These will be also used in the control. The control law has been demonstrated using a very simple example of third order. This is the main result of the paper, saying that, you know, if the system 2 is controlled using the virtual control laws and actual control law in equation 13, then you get some sort of stability. Here is an example that we are interested in. X1 dot equal this x1 square plus x2 cube plus x3 and so on. This is the third order example, and for this example they have provided us the value of alpha 2, alpha 3, which are the same equations that are given in the paper earlier in the generic form. Control law is also given. The parameter values k1, k2, k3 are also given. The initial conditions for the simulation are given, and you can also see that so there will be actually there are 3 state variables, but in simulations we will be using 5 variables because there are 5 differential equations. Z2 and Z3 will also have their own differential equation, which basically z2 dot is equal to alpha 2 minus z2 over tau 2. Similarly, z3 dot will be alpha 3 minus z3 over tau 3. Tau 2 and tau 3 are equal to exponent of minus t plus 0.05. So the tau 2 and tau 3 have same expression. So given all these values, we can now write the code for this system. Okay, so let's go to MATLAB. So first of all, we define the function dx equal, you can name the function. I have named the function backstepping underscore dsc because dsc is the type of control that has been developed. Actually dsc is from here, dynamic surface control. So backstepping, so since this is dynamic surface control, that is why I have named it DSC. Okay, let's go back to the code. So first of all, we'll write the constant parameter values k1, k2, k3, which are given here in the paper. So if you go to the paper here, so k1, k2, k3, they are these values are given, and then we then what we'll do is the desirable reference is given to be sine t. You can see here that the yr is equal to sine t, so its derivative will be also used in the expression for alpha 2. So we'll be needing yr desired, which will be cos t, and then there is this is the expression of alpha 2, which is copied from here in the paper. Similarly, we have the expression for tau 2. Tau 2 is given here. This tau 2 is exponent of minus t plus 0.5. Similarly, tau 3 is equal to tau 2. Then x4 dot, this is the z2 dot. Z2 dot is alpha 2 minus z2. So z2 will be my fourth state variable, and z3 will be my fifth state variable. So I will define two additional state variables, z2 and z3, in the state space because these are the dynamic variables, just like we do in adaptive control. So alpha 3 is given in the paper, so I just copy this expression in the MATLAB. And similarly, z3 dot, this is not given in the paper, but there is enough information in the paper to see that z3 dot is basically alpha 3 minus z3 divided by tau 3. Alright, so go back to the code, and then we have the expression for u, which is also given in the paper, so we just copy it in the code. And then we have x1 dot, which is also you can see here that let's see. Yeah, this is x1 dot, x2 dot, x3 dot. These are all given in the paper, so we just copy it here. X1 dot, x2 dot, x3 dot, same equations as are given in the paper, and finally we define the output of this file to be x1, x2, x3, x4 and x5, where x1, x2, x3 are state variables and x4 is z2 and x5 is z3. So z2 and z3 are low pass filter outputs which is used in the as part of the control design. Now we are ready to write the script file, as we always do. And okay, so first of all, clc, clear all, close all. These are usual commands that I used in order to avoid confusion in the MATLAB. So if there is any figure open already, I want them to be closed. If there is any variable defined, I want it to be cleared, and I want the command window, this window to be clear as well. Then I'll just call the ODE45 function in MATLAB, and using this time limit 0 to 20 seconds, because here in the paper the results given in the paper are from 0 to 20 seconds, so I just want to replicate the results. And the initial conditions 0.8 minus 0.2 1 0 0, these are given in the paper. You can see here that they have provided these initial conditions. The initial condition for x1 is 0.8, x2 is minus 0.2, x3 initial condition is 1, z2 and z3 initial conditions are 0. So same initial conditions applied, and then we plot the results. First of all, we plot the x1 state minus sine t, which is the error plot, which is basically this figure 1, the lower plot of figure 1, x1 minus y reference. This we will plot here. And then we'll grid on is the command that turns on the grid. Then we will plot the x1 and the reference of x1 together in the same plot, and that will give us this plot, which is x1 and reference plotted in the same. Then we will plot all three states in a single figure, which will give us this plot. So all three states in a single plot. Next, in order to plot the control input, as I have done earlier in my previous videos, I will have to actually rewrite all the constant parameters and all the code that has been written here. So I will copy some code from here, and then I will define, this is just initialization of a2 and alpha 2 and alpha 3, but actually what I will use is the for loop, and this is the equation for alpha 2, which is written here. This is the same equation, but there is a difference now. Now we are running the loop from 1 to length of t, which is the all values that have been computed here using ODE45 function. So instead of x1 we will have xi comma 1, and instead of x2 we will have xi comma 2, and instead of x3 we'll have xi comma 3, and so on. And similarly we'll have the same equations as in this file, but we will have these because this is an array, so we will have this index value I included as well. So as usual, if you want to write this code by yourself, just pause the video, take a screenshot, and write the code by yourself. You can also try to write the code as you are watching the video. Just during the video, just pause it as many times as you need to, and write the code as you are watching the video, and by the time you're done with the video you will also be done with the code. So writing the code by yourself gives you a lot of learning. It clears out all your error making habits. So a lot of new students or even expert programmers, they just make errors, including myself. I make errors all the time. So then I debug my code and I just correct it. So this is figure after this all for loop operation, we will have reconstructed the control signal, and then we can plot the control signal, and then we can also plot in figure 5 the z2 x4, the fourth state is z2, and we can compare z2 with alpha 2, and similarly in figure 6 we can compare z3 with alpha 3. So this will give us okay. So this will give us the whole. Now we are just have to run this file. I click the run button and all the 6 figures are right in front of me, and we can analyze the figures one by one. So first of all let's look at this figure. This is error. It has gone to 0, just like if you see here this plot. This corresponds to figure 1 here. So this is figure 1 and this is the plot given in the paper. Similarly this plot, this corresponds to figure 2 that we have plotted. So this is figure 2, and you can see here that these are of course these are similar, and this corresponds to, I think we have figure 4, no, figure 3. So figure 3, this is all 3 states. These are the states that actually in my case I have plotted the all 5 states, but if I want to plot all 3 states only, then all I need to do is go to figure 3, and instead of plotting tx, I can plot t 1 2 3 comma sorry all comma 1 2 3. So this is all rows, and but columns are from 1 to 3 only. So not column 4 and 5 will not be included. So now if I look at figure 3, or still, yeah, now we have only 3 plots. So this is the blue graph is x1, green graph is x2, and the red graph is x3. So you can see here this x2 is red in this paper. In our code it is green, and this is gray in x3. This is red in our code. So you can give it any color you want. Similarly, this is the control graph. So we have this control graph, which looks pretty similar, except for we have some chattering in here, and this graph is smoothed out. So you can I don't know why this difference is. Maybe they just they just maybe applied low pass filter to the control signal, and maybe I did not, but the equation of the control that I used is the same as the one given in the paper. And this is the comparison between alpha 2 and z2. In our case it should be figure 5. So you can see z2 and alpha 2. Again, our plots are not exactly the same as their plot, but the main thing is that z2 is tracking alpha 2 in both the cases. And then similarly z3 and alpha 3, if you look at these plots, this is z3 and alpha 3. This plot looks quite similar to the one in the paper. So that's it guys for now. And recap the video, recap this paper and the code. So in this video we developed code for backstepping based dynamic surface control method, We looked at the paper very briefly, what kind of nonlinear system it considers, what are the underlying assumptions, and then we looked at the control method. It considered like n steps, and then we can also go to there are some intermediate auxiliary variables involving low pass filters, and then there is final control law u, and the example that is given, that is a third order example. Here is the third order nonlinear example that is given in the paper that we have reproduced using all the parameter values and the equations of the auxiliary variables and the control system in the paper. These are the results that we have reproduced, and this is our code. You can see here, this is the main function file where we define all the parameters, write all the equations necessary for defining the control law, write all the state dynamics x1, x2, x3, and then we write the script file which will use the ODE45 function in MATLAB, give the initial conditions, plot the results. In order to plot the control, you have to repeat the equations in the function file with some the indices involved, and then that's it. So these are the results, and this is the code, and the happy learning control systems. Thank you for watching. Please subscribe if you want to uh, keep informed regarding the upcoming videos.